Hi guys, this video describes how the linear recursion pattern can be applied to binary search trees. We're going to use this pattern very soon to define the search operation recursively in binary search trees. First, let's review the linear recursion idea. The linear recursion idea is a pattern for creating recursive functions. So a recursive function in general is a function that could call itself, and there's a lot of risks with recursive functions. You can have them run infinite recursion, or be missing a base case, or perform poorly, or something like that. So the linear recursion pattern is a pattern for writing these in kind of a foolproof way. It's a fill in the blanks kind of a pattern. And the defining structure of a linear recursive function is that in the general case, the function makes exactly one recursive call. So it doesn't call itself 2 times or 3 times or something like that. It calls itself just once in the general case, and it calls itself on an input that's smaller by one piece. So we saw examples of linear recursive functions that operate on integers like factorial, and the way that factorial works is it's given an int n and it calls itself on an int n minus 1, thereby making the input one piece smaller. And then we've seen a lot of examples of linear recursion on singly linked lists. And in the general case, a linear recursive function on a singly linked list calls itself on the remainder of the list. So all of the nodes after the first one. And that makes effectively the node chain one smaller. So this here is some very abstract pseudocode that gets the idea across. If you're writing a linear recursive function, it's given input. And if we're in the base case, we return the base case solution. That's to make sure that there is a base case that's evaluated first. And in that base case, there's no recursive calls. The function just ends. That helps with preventing infinite recursion. And then in the general case, where we get past the return statement, the function calls itself once on smaller input. We call the output of that a sub-solution. It's the output of everything in the smaller input. And then finally, we produce a general solution that involves that sub-solution, but it also has to incorporate the one little piece that we eliminated from the recursive call. So in the case of singly linked lists, the recursive call is on the first nodes next, so that's all the nodes after the first one, and we need to incorporate the first node somehow into the overall general solution. So let's see how we could apply this pattern to a binary search tree node. So filling in some blanks here, a recursive function that does linear recursion on a binary search tree node would have the same kind of base case situation. We'd say if we're in a base case, we just immediately return a base case solution and do no recursion. But then if we're in the general case, we call this function on a smaller input of some kind, and the same thing applies. You get a sub-solution and incorporate that to make a general solution. Well, a binary search tree node has 2 pointers, so we could kind of go in 2 directions. If we're at 61 here, we could go left or we could go right, and that's what we're going to do in this recursive function call, is we're going to go either into the left pointer or into the right pointer. So every recursive call is one level lower. Remember, the idea of linear recursion is every time you call the function on itself, it's being called on a structure that's one unit smaller than we had to begin with. So in binary search trees, linear recursion, we're going to think of levels. So this tree kind of has 3 levels. There's the root level, 37, then the second level down, and the third level down. And every time this recursive function is called, it's on a shorter tree that has one fewer level. So the base case then is usually null pointer. That means you went below a leaf node. So remember, the root is at the top here. Every recursive call is going to go lower into the tree by 1 step until it gets to the bottom of the tree. And the bottommost nodes are called leaves, and leaf nodes have no child pointers. So when you go past a child pointer, you have a pointer to a null node. You have nothing at all. So ordinarily, the base case is if the pointer to a node we're given is null, that means we've reached the null pointers below the leaf nodes, then we return some kind of base case solution. And the smaller input is usually a child node. It's usually either the left child or the right child, and some kind of decision making has to happen in here to decide which of the 2 to follow. So here is, again, some kind of code, but with some fill in the blanks for how we could write one of these functions. So this is just called func function. The input to the function is a pointer to a node. It has some return type. The underlining means that's a fill in the blank, so you would have to replace that with the return type of the function. and we say if not where, then return the base case solution. This Boolean expression uses the fact that a empty shared pointer, otherwise known as a null shared pointer, is false when converted to a Boolean and true when the pointer is pointing at an actual node. So this says if not where means if where is pointing at null, nothing, then we're in the base case and return a solution there. We've got an underlined fill in the blank. Otherwise, we create the sub-solution, but we have to decide if we're going to make a recursive call on the left child or the right child. So I declare the same return type called sub-solution, and if we decide to go left, then the sub-solution is equal to the recursive function call on where's left. Else, meaning we did not decide to go left, so by default we decided to go right, then sub-solution is equal to the function call on where's right. So sub-solution is initially initialized, and then we make a decision. Are we going to go into the left child recursively or the right child recursively? Depending on that decision, we still only make one recursive function call, and it will be on one level lower in the tree. And then the same general solution stuff happens at the end. The sub-solution has been initialized with some contents from lower in the tree, and then we need to incorporate that with the node we're at, the where node.